Good morning, dragons. I'm excited to be starting a brand new lesson with you. We're going to work on some one-step addition equations. So we're in the algebra unit. We're in the equations section of the algebra unit. Hopefully you already completed your warm-up, which was on a Google form assignment for you, and it is graded. So hopefully you got to that. If you didn't, please get to that. So we are looking at some important vocabulary today. We've got a bar model, which is super helpful visual model for algebra, and I love it, and I wish they had it when I was a kid, but they did not. One-step equations, and we're going to also talk about inverse operations. So these are your important vocabulary terms. And I'll explain all of them as we go. I'm going to skip over the getting started section today. I'm going to dive right into the lesson. I'm going to be using a couple colors today, so if you have any crayons or markers or colored pencils, I think I'm going to go with some blue, some red, and I'm looking for a green that's going to show up on the screen for you. How about that? Let's do that. Okay, so I'm going to use some colors today to help illustrate and accentuate the bar model more. Let's take a look. Let's read together. Reasoning about equations and determining solutions with bar models provides a visual representation of the structure of the equations. A bar model uses rectangular bars to represent known and unknown quantities. All right, highlight your new vocabulary word. I'm going to come over to the side text. Remember, a solution to an equation is a value for the variable that makes the equation a true statement. That brings me back to lesson 1. Sometimes true, always true, never true. We want this to be always true. Always true. Okay, going to put a little note there for myself. All right, so they've got a nice example for us, and I'm going to see if we can color code it in a meaningful way. So let's consider the addition equation x, our variable, plus 10, our constant, equals 15. So they're saying that this equals it. It's a true statement. And there you've got two bars here. They're saying x plus 10 bar is the exact same thing as having the number 15. So if I were to illustrate that, that's like saying this guy contains the exact same value as this guy. All right, fair enough. That guy is equal to that guy. This equation states that for some value of x, the expression x plus 10 is equal to 15. This can be represented using a bar model. This guy, this is your bar model, if you weren't sure. Hello, I'm a bar model. Okay. Just like with area models, which you have done using the distributive property, bar models can be decomposed. Love that. I was hoping they were going to use that word. The expression x plus 10 can be decomposed into a part representing an x and a part representing 10. The number 15 can be decomposed in a similar way. So I am decomposing from here to here. We're going to decompose. But they did this in a meaningful way. What do I mean by that? We can see that x plus 10 becomes an x and a 10. I think that's fairly reasonable for all of us. So that guy's 10. So it makes sense that if this is a green 10 box, then this is also a green 10 box. And they're saying, hey, decompose 15 as well. All right. Well, if I did, I must have done some mathematical thinking to go from here to here and decompose it. So what am I thinking? Let's zoom in on this for a second. I understood that x plus 10 became an x and a 10. And x is my variable, so I'm going to go ahead and put him in red. And I kind of understood that 15 could be broken up. And 15 could become 10. But then I needed a leftover corresponding part that would match with the x. What would match with the x, but still result in addition sentence that got me 15? The only possible thing that could have existed here was 5. So that means the green 10 matches with the green 10, and now x matches with the red 5. Where's the thinking there? What is happening? Your think bubble says, well, I had 15, and I knew I had to take away 10. I had 15, and I knew I had to take away 10. So I only had a possible solution. So if 15 took away 10, that was going to leave me with who? It's going to leave me kind of with two different things in this particular scenario. It's going to tell me the value of x, but it's telling me that x has a very distinct value. That x is 5. That's what's happening. I'm saying the blue bar is worth 15. I'm going to section out a part of it that's worth only 10. So what is the other section worth? It had to be 5. Let's see what else they say for us. The bar model demonstrates that these two equations are equivalent. That x plus 10 equals 15 is the same as x plus 10 equals 5 plus 10. You're going, huh? What are they talking about? They're saying, wishing I had an index card. They are saying that these two guys are equal, and these two guys are equal. So the blue and the blue are equal, and then our red-green combinations are also equal. That's what they're saying. So we can color code that to make that easier for you. So we're saying blue is to blue. Those are equal. And then we're saying this guy is equal to that guy. By examining the structure of the second equation, you can see that 5 is the value of x that makes this equation true. Side note. Because the expressions x plus 10 and 15 are equal, their bars are of equal length. Even after the bars are decomposed, the lengths maintain their equality. You're dealing with unknowns. Do not worry if the lengths of the parts are not accurate. I think they're saying there, in this particular case, they are drawn to scale. But they may not always be drawn to scale. I find, though, in the bar model, that it usually is. Why do you think the number 15 decomposed into the numeric expression 5 plus 10? Why wasn't it 7 plus 8? Why not? Think about that for a moment. The number 15 is decomposed into the numeric expression 5 plus 10 to mirror the structure of the expression x plus 10. let's see if I got my thought down correctly. The number 15 is decomposed into the numeric expression 5 plus 10 to mirror the structure of the expression x plus 10. So if x plus 10 looked like this, and I needed 15 to look similar, like if this was going to break up, I would have needed part of it to be worth 10, which would have left part of it being the mystery part. That would have been the 5. Here, I'll leave it there for a second if you need to get those notes. All right, our character over here says, notice how the bars maintain the same length throughout the entire model. That's true. That's kind of the intention of the bar model. Describe how the model in the worked example would be different for each equation. Complete the bar model for each. We're going to be decomposing these. So if the blue, x plus 10, is equal to the blue, 17, and we decompose it, the green has to be equal to the other green. Does it not? We're trying to be consistent. So this green has to be worth how much? What do you suspect there? If you said 10, you did excellent work. So we've got 10 there because we want the green to match the green. Now we need the red to match the red. This is your variable. He is the missing part. He is the unknown. The unknown. Well, we need him to match this guy. We need a value for this guy. What is the thinking bubble? The thinking bubble says, it says 17 minus 10 equals something. I already have 10 of it. Now I need the remaining part of it. So it must be worth how much? It must be worth 7. What does that mean to us mathematically? It means that x plus 10 equals 17. It also means that x plus 10 equals 7 plus 10. And it means one more thing, that x itself is equal to 7. Try B on your own. Take a moment and pause the video. Try to color code it and solve B all on your own. Hopefully you took a moment to solve B, and I'm going to walk you through it, just like I walked you through A. So we've got x plus 6 in the blue. He contains the same value as this other blue box, 15. We have to decompose here, and if we do that, we need green to equal green. Well, the only thing that makes sense for this one is 6, because the x is already here. They took the x out, so this has to be 6. Well, if this green is 6, then this green is 6. Now we have red. Our unknown is x. What had to be here? To contain the equality, to maintain the equality. The thinking box says 15 minus 6 equals something. What is that something that you found? Hopefully you found 9. That's because 9 plus 6 equals 15. Altogether, what is it saying? It says that x plus 6 equals 15. It's also saying that x plus 6 equals 9 plus 6. And lastly, it is giving the value for the unknown variable. It is telling us that x is in fact worth 9. The reds match. If you have questions, be prepared during our live session to ask your questions. Perhaps write a note to the side or grab yourself a sticky note and write down any questions you have, any confusion you're experiencing. Number 3, consider the equation 14 plus x equals 32. it wants you to complete the bar model, write the equation represented by the decomposed expressions in the bar model, which value for x makes the equation a true statement. So we've got a three-parter here, but we've walked through all these parts previously. So take a moment, pause your video, and work out number 3. Okay, hopefully you took a moment to work out number 3 and test that out on your own. I'm going to walk you through it like I walked through the others. We start out with 14 plus x is equal to 32. We want to first decompose 14 plus x. Let's start there. I can make this guy 14 and this guy x. What did I do from here to here? I decomposed. I decomposed the structure. So I need to decompose the structure here as well. Well, let's think. If I make this guy green, then I need to make this guy green. And I know they should be a match. So this guy must be worth 14. Well, if this guy's red, I want to make this guy red. And now I need my thinking bubble. What am I thinking? I am thinking that the red is whatever 32 minus 14 is. 32 minus 14 is how much, friends? Can we figure that out? Not sure? That's okay. Perhaps that'll help. So the missing component must be 18. Write the equation represented by the decomposed expressions in the bar model. What are they asking for? This is the blue to blue. The original equation. One expression equal to another expression. We've got one expression equal to another expression. Equations are made up of expressions. Well, we changed it from blue to blue to our red-green combo. So I really have this happening here. I'm saying whatever this combination was is equal to that combination as well. Well, what was that combination? We had a 14 plus x, which is one of the original expressions. But the second expression is now the decomposed version of 32, which is 14 plus 18. Decomposed version of 32. That's your new expression. Which value for x makes the equation a true statement? X had to be equal to how much? It had to be equal to 18. All right, Dragons, you have done a fantastic job, and you might need to pause this again or rewatch it to get all the notes down. And we will finish it 4 and 5 and work together on activity 2.2 during our live session. So thank you for joining me for your mini lesson, and I'll see you soon.